Okay, so today we are going to be looking at a new topic, another amazing piece of organic chemistry, and it's called phenols. Now, a phenol is when you have a hydroxyl group or a OH group directly attached to the benzene ring, just like this. It's directly attached to the benzene ring. Now, most people, when they see, let's say we have a branch coming off, let's say we have this right over here, an OH. So over here, the OH group, the hydroxyl group, is not really directly coming off the benzene. There are actually two carbons over here, so carbon number 1, carbon number 2, and this is going to be simple. This is simply alcohol, so it's not really a phenol. And as an alcohol, because of the functional group, we prioritize the functional group, and it would be the parent compound. This is ethanol, so the parent compound is ethanol, and our substituent, as the benzene ring as a substituent, is again called a phenyl, and it's attached to carbon number 2. Therefore, this is going to be 2-phenyl ethanol. Now, here the main point to just main point to take in over here is that the OH group has to be directly attached to the benzene ring for it to be a phenol. Now, moving on and going on about naming these phenols. So let's say we have an OH group over here, and we have a NO2 nitro over here. So how would you name this? Well, our phenol would be the parent compound, and whenever the phenol is a parent compound, it would always be attached to carbon number 1. So over here, if this attached to carbon number 1, and we name we number the carbons, the nitro would be attached to the third carbon, and so this would be called 3-nitro. And if we don't need to write the 1 down, so it would be 3-nitro phenol. Now moving on to the second example, let's say we have an OH group. So again, our phenol is the parent compound, is attached to carbon number 1. Whenever it is the parent compound, it's always attached to carbon number 1, as I said previously. So if we number this 1, 2, 3, 4, 5, 6, so this is going to be called 2, 2, 4, 6 tribromo. There are 3 bromides, tribromo phenol. Okay, so now moving on to our third example, and this is actually to do with the exceptions. So then the exceptions were benzaldehyde, when you have an aldehyde functional group attached to the benzene, a phenyl amine when you have a amine group attached to the benzene, and a benzoic acid, so when you have a carboxylic group attached to the benzene ring. So if we have one of the exceptions, let's say we have our amine group NH2, and we have our a phenol OH hydroxyl group. So as I said, the exceptions have to be prioritized, and they are always attached to carbon number 1. So over here, our parent compound would be phenyl amine, because we prioritize our exception. So if I write our parent compound down, phenyl amine, and if we number the carbons, a 1, 2, 3, and as a substituent, hydroxyl group, as a substituent, it is called hydroxy. So over here, this is going to be called 3, attached to carbon number 3, 3-hydroxy phenyl amine. Now, the main key point over here is that as a substituent, our hydroxyl group is called hydroxy. Okay, so now moving on to the reactions. Now, our phenol can act as a very weak acid, and it has a pH of approximately 5, really depending on the concentration, and this is shown by the dissociation of phenol in solutions. Okay, so as I said, this is shown by the dissociation of phenol in solution. So if I have a phenol over here, OH plus, not plus, so phenol, and this would dissociate in solution to form this ion over here, so O minus plus a proton H plus. So the hydrogen in this hydroxyl group is our acidic proton, and it's released at the end as a H plus ion. Now this ion over here is actually called a phenoxide ion. Okay, so now we'll look at the acid and base reaction of phenol. So because we can actually do an acid and base reaction, as it is a weak acid. So acid plus base, an acid and a base react to form salt plus water. So over here we are expected to form a salt and water. So if we have our phenol over here plus let's say any base, potassium hydroxide, and we'll form a salt. So the hydrogen would be replaced by the metal ion, so O minus, and we'll write it like this. Or we can actually write this like this. However, these aren't bonded together, so you can't put the bond in between. You have to show that this is ionic. Now, and plus a H2 molecule, because it does form water as well. Now, what is this ion called over here? What is this called? So, as I said over here, this is called a phenoxide ion, and we have a potassium attached over here. So this would simply be called potassium phenoxide. Now, if we used sodium hydroxide instead of potassium hydroxide, this was going to be called sodium phenoxide. Okay, so now we'll be comparing the reactivity of phenols to a weak acid, and a weak acid is carboxylic acid. And because the phenols also have that hydroxyl group, it would be reasonable to compare it with alcohols. So firstly, if we compare it to alcohol, okay, so our alcohols are not acidic at all. They have a pH of approximately 7, and they don't react with strong or weak bases. And our strong base in this case is sodium hydroxide, and our weak base is sodium carbonate. And you can have any carbonate, lithium carbonate, potassium carbonate. So alcohols are not acidic at all. Okay, so moving on to our phenols. Now, phenols are weakly acidic, as I previously said, and therefore they only react with strong bases. So in this case, sodium hydroxide only, and they wouldn't react with weak bases. When you react a phenol with a weak base, there would be no reaction. So moving on to our carboxylic acids. Now our carboxylic acids are weak acids. They have a pH of approximately 3. However, they are weak acids, but they are stronger than phenols, and therefore they react with strong bases and weak bases. So in this case, they react with sodium hydroxide, and they would react with our carbonate, so sodium carbonate in this case. Okay, so now our phenol also undergoes electrophilic substitution, and it reacts different to benzene. And well, why does it react different to benzene? Well, there's evidence for that. So the first evidence is the bromination. So if we have our phenol OH plus Br2, we will form this over here, so OH. So now, the reagents and conditions for this is, well, phenol is more reactive than benzene, and therefore it doesn't require a halogen carrier. Well, why is it more reactive? And well, we'll focus on that section in a later video. We'll compare benzene and phenols. So here, as you can see, this has undergone 3 substitution reactions. Therefore, we need to put 3 over here to balance the equation, and it is electrophilic substitution reaction. Therefore, we also form 2 products, so plus HBr, and again 3 over here. So the condition for this is it only undergoes room temperature and pressure. It doesn't require a halogen carrier, as phenol is more reactive than benzene. Now, the observations you'll see in this reaction, well, if I just write it down over here, observations. Okay, so observation you'll see is that a white precipitate forms. So a white precipitate forms as this compound over here. So if we just name this compound, which would be 2,4,6 tribromophenol. So our 2,4,6 tribromophenol would form a white precipitate as it is a solid. So as you know, bromine is orange. It's an orange and brownish liquid. So at the end, the phenol decolorizes the bromine water, and these are the observations that you'll see. Okay, so moving on to the second piece of evidence, so which is the nitration of phenol. So if we carry out this reaction, and remember when we were doing the nitration of benzene, we used a concentrated nitric acid, and we used a catalyst, a concentrated sulfuric acid, and it was carried out at 50 degrees Celsius, I believe that was the condition. So over here, we actually use dilute nitric acid. So as you can see, the conditions are much milder when you're using phenols, and it's carried out at room temperature and pressure. So now there are actually 2 compounds we can form. We can form this over here, so the nitro can be on carbon number 2, or we can form this over here, it can be on carbon number 4. It really depends how it reacts. So plus a H2O molecule.